Hey everyone, welcome back. Today we are talking about consistent hashing, a special hashing technique that helps distribute data efficiently across clusters of servers. If you want to ensure scalability while minimizing data reshuffling, this technique is for you. Let's dive in. As always, we answer the what question. So, what is exactly consistent hashing? Consistent, consistent hashing is a method of assigning data to servers or nodes in such a way that only a small portion of data needs to be moved or reassigned when servers are added or removed. This is crucial for large scale system where you want one, scale out by adding more servers, two, handle failures if a server goes down, three, minimize the cost of rebalancing data. Traditional hashing methods can cause major data movement when the cluster size changes. Consistent hashing solve that problem while with a clever approach. Okay, how does it work? Okay, let's see this example. So we have a hash space, and this hash space is that ring that you can see. Like imagine a circular space or ring numbered from 0 to 2 in the power of n minus 1. This is our hash space. So we have a hash space, and we have the node 1, node 2, node 3, node 4, which represent the servers, and we have key 1 and key 2, which represent data. Number two, we have mapping servers. Like each server or node is assigned one or more hash values that place it at certain points on the ring using a hash function, as you can see. After that, we have mapping data. Like each data item, like key 1 and key 2, is also hashed to the same on the same ring. Okay, so the data are on the same ring with the servers. All right, we need to understand how data assignment will work. Like you store each data or data item on first server you encounter when move clockwise around the ring from the item's position. Like we go, if we want to know how key 1 where it will be stored, it will be stored in key 2. We go clockwise. Here we go clockwise. If we have another one here, it will let's make it like that. If we have another one here, it will go clockwise as well. Okay, what are the benefits from that? First, minimal data movement. Like when you add or remove nodes, only the data bounced by the node's range on the ring needs to move. Number two, it's easily to scale. Like adding more servers is as simple as calculating their hash position. You will only shuffle a small subset of data. So, if for example, if we want to add a new server here, like let's change the color, a new server here, key 1 will be reassigned to this new server, and all the other data and servers will still remain like they will not be affected at all. So it's easy to add more servers. Also, it's fault tolerant because if a node goes down, like let's say that node in let's say that n3 goes down. If n3 goes down, only the data mapped to the node needs to find a new location on the ring. So let's see that this is key 3. Key 3 will be mapped to n4. Also, we have what we call event load distribution, because with the proper hashing and possibly using virtual nodes, and virtual nodes like n1 has one position here, we can add another position here, and we call it n1/1 to add maybe virtual nodes. The load will spread out evenly across all servers. These factors make consistent hashing ideal for distributed caches, sharded databases, and larger scale systems like NoSQL stores. Okay. Um, we need to talk about the handling server changes. It's a pretty important thing. So let's go back. So if you add a new server, let's call we have let's take this. Let's change the color. Let's say that we add a new server. Like let's say that we add a server here because this is the only place which is available. We add a new server here, okay? And we give it a hash value like 450. Only the items that fall between the previous node and the new node, which with this is we call it in this is let's call this M5. All that, let's say that also we have a new key. Okay, so this is key 4, I guess. So, okay, here, if you add this N5, okay, and all the data that is fall between N1 and N2 will be affected. And they will need to be migrated. So if we have no N5, the key 4 will be stored in N2, but when we add N5, key 4 will store in N5. Okay, so the items mapped to N2 that falls in this position, it will map to N5. This localized movement is what makes consistent hashing so powerful for dynamic environments. Also, we can use virtual nodes. Let's assume that N1 has a bigger capacity than all the other servers. So what we can do is that we can add more servers, more versions of N1. Let's change the color. No. We can add more versions of N1. Okay, let's say call the N1/1. So we have two versions here of N1, and when we have data, let's refer to a keys like something like that, smaller, so we can have when we have data we can store them there as well. Some implementations use virtual nodes, as you can see here, where each physical server is assigned multiple points on the ring. This helps handle cases where servers have different capacities or you want an even load distribution without any hotspots. Effectively, each server is replicated at multiple ring positions, smoothing out any imbalances. Okay, what are the use cases for consistent hashing? First thing, it's used in distributed caching. It's used in sharded databases. It is used in load balancing for microservices. It is used for large-scale key value stores. Consistent hashing is go-to solution in many modern large-scale systems where you want to manage data across clusters gracefully. Okay, so final thoughts. Consistent hashing in a nutshell, by placing servers and data on a hash ring, and only remapping a small slice of data when nodes change, you get first scalable growth, second minimal rebalancing, and lastly even load distribution. If you're designing distributed system with shifting server counts, consistent hashing is a game changer to keep that overhead. So thanks for watching this video, and see you in future videos.